Let's have a look at the question 27 at the end of the chapter 9. And this one is asking us for what massive product forms from a decomposition reaction. And the compound that's decomposing is ammonium carbonate, right here, ammonium carbonate. And it says ammonium carbonate decomposes to form ammonia gas, carbon dioxide gas, and water vapor. What mass of NH3 gas, there's your ammonia, is formed when 1.25 grams of ammonium carbonate decomposes? So when you see the word ammonium and hear the suffix ium, that denotes your positive charge. Ammonium, you should remember, is NH4 plus. So that is your one and only polyatomic cation, positive ion, that we cover in this course. Carbonate, CO3 2 minus, another polyatomic ion, this one, the anion. So NH4 plus and CO3 2 minus. How are they going to go together to give you a molecular formula? NH4 plus, CO3 2 minus. Right, so you're going to need two ammoniums. So that would be NH4 in brackets with a 2 outside and CO3. So there's my solid, it decomposes. This stuff is actually smelling salts. People think that it just sublimes, but it doesn't. It actually decomposes. And ammonia gas, you got it, pretty gross and stinky. Carbon dioxide and water vapor, otherwise harmless. So not very much, 1.25 grams decomposing, and that'll wake you up. Smelling salts. So this is what's given, 1.25 grams. They, I think in the textbook they actually gave you the equation, but again, just to step it up to an expectation that we would have of us on a test or exam. Now you might be thinking, well, hold on, because ammonia gas, are we supposed to know ammonia gas? Read the rest of the question. What mass of NH3 gas, well, is formed? Clearly then this NH3 guy is a product, but we said the products are ammonia, carbon dioxide, water. So yeah, if you think something is missing, always go back and try and make sense of that. Okay, so you want to start with an equation, actually. You want to start with an equation, and of course you don't want to start any calculations until you have a balanced equation. So the way that I would advise you to do this is to go from words to formulas and then balance. So ammonium carbonate, we've just established, is NH4 CO3. It's the solid. It's decomposing to form these three gases. You see the driving force here is the production of gas, for sure. And at first, it may look a bit intimidating to actually balance this. And I skipped over this part here, CO2, H2O, of course you know, carbon dioxide and water. So how did you go about balancing? Oxygen appears once on the left, twice on the right. Could be tricky. Don't want to do that one first. Carbon, it's 1 and 1. That seems okay so far. Nitrogen, there were 2 on the left. There was 1 on the right. And then hydrogen, again, didn't want to start with it because it appears twice on the right-hand side. So that's why I balanced the nitrogen first. And as it turns out, as soon as I put that 2 to balance the nitrogen, I actually was in good shape because that 2 outside tells me I have 2 N's and then 2 times 4, 8 hydrogens. And if you look on the other side, The 2 in front of the ammonia gas then tells me that I have 6 hydrogens in that ammonia gas, right? 2 times 3 is 6 plus, and then the water, 2 more. So 6 and 2 is 8. So actually that's balanced. You're given 1.25 grams of this starting material, and you want to find out what is the mass of ammonia gas that's produced. So this question could be asking you for what mass of each gas is produced, and we would just duplicate the calculation that you're about to see for ammonia for each of ammonia, CO2, and H2O. And you know it, as soon as you have a mass, you're going to convert to moles. So we need to look up the molar mass of ammonium carbonate on the periodic table. It's not there, but what is nitrogen? So we want, how many nitrogens are we adding up? 2 nitrogens, how many H? 8 hydrogens, 1 carbon, 3 oxygens. Okay, so 2 times 14.01, 8 times 1.0079, 1, and you're adding to that again, 12.011 for carbon, and 3 of the 14.999, or 15.999, sorry, oxygen. Anyway, use your periodic table, and I got 96.09 grams. So again, because I'm keeping this in line here with the compound, I didn't put 1.25 grams of NH42CO3 just to, I didn't want to clutter it. So I know that I'm talking about ammonium carbonate, and I'm keeping it underneath. So 1.25 grams times 1 mole of this stuff is 96.09 grams. So there's my number of moles, 0.0130 moles of ammonium carbonate. Finish the question then. Use your balanced chemical equation to create your conversion factor. What are you converting from to? Moles of ammonium carbonate to moles of ammonia gas. So in terms of a conversion pathway, you're going from you're given a mass of ammonium acetate to moles of ammonium acetate to moles of ammonia gas to mass of ammonia gas. So you can't actually convert from species to species, let's say from this guy to this guy in terms of amounts. You can only convert moles, okay? Because of that balanced molar ratio. So in this case, it's 1 to 2 to 1 to 1 throughout that reaction. I have 0.0130, keeping 3 sig figs, moles of ammonium acetate. Here I am writing my ammonium acetate because my calculation involves 2 species. My conversion factor here is 2 moles NH3 over 1 mole. Where did that come from? Look up above at your balanced equation. I know that 2 moles of ammonia form for every 1 mole of ammonium acetate consumed. So if I want to convert from ammonium acetate to ammonium acetate to ammonia gas, I'm using the conversion factor derived from a balanced equation. So you see how my complete units here will cancel. So basically I'm doubling that number of moles to 0.0260 moles of ammonia. I could have put this and I would have put this conversion factor immediately here, multiply by. I didn't have to stop in between, but I'm instructing here and I just want to make sure we're carrying everyone along. So that's the moles of ammonia, and then a second calculation to convert the moles of ammonia gas to a mass of ammonia gas. This is the molar mass. 1 mole of NH3 is this many grams. Look at your periodic table. 1 mole of N, 3 moles of H add up to 17.03. And when you do this calculation, you get this number. Trim it back to 3 sig figs. Yes, 3, because that 0 means something. And 0.443 grams of ammonia is produced. Now, I said in the beginning, the question could have asked what mass of each gas is produced. So the first step would be the same, but then here, once you calculated this, you would go back and say, all right, now I want to convert from ammonium acetate to the number of moles of CO2, and I would have 1 mole of CO2 per 1 mole of ammonium acetate and carry on, or for water, 1 mole of water vapor per 1 mole of ammonium acetate consumed and carry on again. So that's the extent of that question. Pretty straightforward. Notice here that although we're in chapter 9 and we're talking about limiting reagents, this is a decomposition reaction. So this is why we're not talking about anything limiting, because how many reactants do you have? 1. So the reaction's going to run out when this thing completely decomposes. So yes, that we are assuming that the reaction goes 100% and there wouldn't be any ammonium acetate remaining, any residual. So that's it. There you go.